Alright, so we're going to keep going with Newton's second law, and we looked at how we can use it to solve for weight and things moving in the vertical direction. Now we're going to kind of combine things. So instead of just having one object moving vertically or just having one object moving horizontally, we're going to have a system of objects connected that are moving together. Okay? And it doesn't mean anything has to change. Okay? So we're still going to do a lot of the same stuff. Same laws. Okay? It's still Newton's first, second, third law. Free body diagrams are still your best tool for solving these problems. Okay, and a couple things you have to keep in mind. These 2 points. Keep objects separate and keep direction separate. Okay, you cannot add an x velocity to a y velocity. You cannot add an x force to a y force. Gravity pulls down, the normal force pushes up. You can combine those. But if tension's pulling to the right, that has no effect on gravity at all. So you can't combine forces that are at 90 degrees to each other.
So we're going to be labeling everything x and y. We can combine x's, but we can't combine anything with y's. And you'll see that when we do problems.
Yeah. And so this part right here, use clear and uniform notation. It doesn't really matter to me what it is as long as you know what you're doing. Okay, and one more time, pay attention to the different directions and different objects. So there's lots of stuff that's going to happen. You got to keep it all separate. Okay, so let's take a look at a problem. Okay, and our object here is we've got this cart. We call it M1. It has a mass. It's being pulled by a hanging mass, M2. And what we really are interested in on this one is the acceleration. Okay, we want to know how fast is this going to accelerate. Okay, and of course, at first we think, well, let's just take a look at each object. Okay, because if we zoom in on that thing, we know M2, there's forces here. There's the rope pulling up and there's gravity pulling down. So we think we can deal with that. Okay, but then we realize the rope is also connected over here at M1, and so then there's other forces. There's gravity and there's the normal force and there's tension. Okay, so what we do is we take each object individually and we start analyzing all those different forces. So here I've just grabbed our 2 masses. Okay, so here's our cart sitting on the track. What forces do we have on it?
Okay, so in the x direction, which is our horizontal direction, okay. I'm assuming we're mass or frictionless.
We are frictionless.
We're going with tension, pulling.
Okay. Right. So this rope right here has some tension in it.
Label that FT.
FT.
And then since there is no friction, there is no opposing force to that. So that's going to be an unbalanced force.
That's going to be an unbalanced force. There is nothing else acting on that. Okay. So if we do FT. Okay, there's no other x forces. Are there any other forces?
There are forces in the y direction. There's going to be the normal force and weight. So normal force perpendicular to the surface,
Fn,
and weight or Fg.
Fg here.
Going down.
All right. So that's object 1. Okay, and over here we have object 2.
Okay, object 2 is going to have tension again going up.
Now, this is a different object. Do I need to call this tension a different tension?
You do not, because remember, if you take 2 force probes and you stick a string in between them and you pull them, no matter what, they're all both reading the same number.
Since the rope is connected, it's one solid rope. Newton's third law, if I pull on it, it pulls back the same.
That's going to make things nice because Ft is the same on object 1 and object 2. And then you got Fg going down.
Okay,
so you got to be careful because it's different than that Fg over there. So it might be nice to put a
F2G, and over
1,
here
maybe.
we should do F1G. Okay, so that's how we can distinguish F1G. That's the weight of this cart. F2G is the weight of this mass. And unless the masses are the same, they don't have the same weight. Okay,
right, so we're going to have to distinguish those.
All right. Now, what we want to do is we want to figure out the acceleration of these objects. Now, they're connected by this rope, so they're going to have the same acceleration, but in different directions. So I guess we need to establish our directions. This cart is just going to accelerate this direction, and
so
that's
make that
positive x. Okay, and this mass is going to fall this way, and that's down, so we'll call that negative y.
That makes sense.
Okay, and so now let's actually do the analysis. Let's see what we got. So we said we can't mix directions, so we're going to start in the horizontal direction.
Okay, horizontal is the x direction.
Horizontal is the x direction. Okay, so if we start in the horizontal direction, we start with object 1. Okay. Newton's second law,
sum
net
of the force
equals mass times acceleration. But we've got to tailor this to this thing. Okay,
so there is only one
force.
force.
Net force in the x direction of object 1 It is mass 1. Now, mass doesn't need an x or a y because mass is not a vector quantity.
Mass is mass.
Okay, acceleration, though.
Acceleration, 1 in the x direction.
1 in the x direction. Okay. So now if we look at that, there's only one, like you said.
So we can just say ft equals
m1 a1x. Okay. Now, if we come over to this object in the horizontal direction,
that object's going to be nice because it's only going down. It's not going to move left or right.
So net force 2 in the x direction is
nothing.
There is nothing.
So
nothing to worry about there.
Okay.
All right. So now we're going to go to the vertical direction. Okay. Same process. Object 1, net force in y
is equal to.
Let's see, we got the normal force
minus F1g
equals.
It's going to be 0 because it's not moving up or down.
Right, it's not accelerating off the track, so this is just 0.
So that's 0.
So that's 0. We don't have to care about that one. All right, so this one.
This one we will have to care about because it is going to accelerate downward.
Okay, so net force on object 2 in the y direction
is equal to. Mass
Ft.
Okay, we can go Ft minus F2g.
F2g
equals then mass 2 acceleration 2y.
2y. Okay.
So the second object, and we're in the y direction.
All right. Now, what we have is these two equations are both going to 0, so we're not worried about that. We want the acceleration, and we see an acceleration in this equation and in this equation, but both of them, there's two unknowns, so we've got to figure out a way to combine these. Okay, so if we jump over to this is when you have two equations and two unknowns, you're actually in a pretty good shape. Okay, so we have from before the tension force is actually equal to m1 a1x, and we also have that the net force in the y direction on object 2 is equal to Ft minus F2g, which is equal to m2a2y. Okay. Now, what's F2g?
Okay, that's the weight, so we can even substitute in again. Minus m2g
equals m2a2y. Now, we're still a little bit in trouble because I have Ft here and Ft here, which is good. M's are known, we'll know masses. Acceleration, but a different acceleration. But if we take a look at what's actually happening, this thing is accelerating this one, right? This is a1x. This one is accelerating this way. This is a2y. Okay, is there a relationship there?
But if you think about that, they're accelerating with each other, right?
The string is holding them together. So whatever this one accelerates at, this one accelerates at.
So their magnitudes are going to be the same. Like the size of it, and we need to think about their direction.
Right. So this one's actually going to accelerate in a positive direction, but that
one's going in a negative direction, but it's still going to be the same
size, just different direction. So really we could say a1x is equal to negative a2y, or either way, a2y equals negative a1x. Okay, so we have that relationship. So we actually have a third equation to get in here. So I'm going to go ahead and I'm going to write that one as well. a1x, negative a1x equals a2y. Okay, well, if we take this equation for Ft and plug it in over here, we're going to eliminate one of these equations. So I'm going to go ahead and do that. So I have m1 a1x minus m2g equals, and now I'm going to make this substitution as well.
Okay.
So a2y becomes negative a1x. So I have negative m2 a1x. Okay? And now we just have to combine like terms. So I'll add this thing over here to get it with this a1x. So I have m1 a1x plus m2 a1x. And I can go ahead and add this to the other side,
so
m2g. And since we want acceleration, we need to undistribute that.
So factor it out.
So m1 plus m2. And just to simplify things, I'm just going to say, since we got I guess I can keep going. a1x equals m2g. And now I can divide both sides. So the acceleration in the x direction is equal to the total, the m2g, which is a force actually, divided by the total mass of the whole thing. Okay. Now remember, this was for a system of objects. A system of objects is a set of multiple things that have are connected. They're acting together. Okay. So if we look at that, that's actually just Newton's second law.
Can you explain that?
Yeah, well, okay, so we got a1x equals m2g, m1 plus m2. Let's go all the way back to the first picture and see what we have. I have a1x equals m2g over m1 plus m2, right? All right, so a1x is acceleration. M1 plus M2, well, that's
a mass.
That's what mass is it? Well,
mass
it's the mass of
the system, I guess.
All of that stuff. Yeah, it's the mass of the system. Well, this acceleration, that's really the acceleration of the system because we said this and this, they're the same magnitude. And M2G, that's the force that's actually pulling this thing down, making the whole system accelerate.
Or the weight of
this thing, okay? So that we really have is just Newton's second law. Net force equals mass times acceleration, okay? So that is how you, I mean, that answer makes sense. So we can get the acceleration, okay? Which, if you look at it in those terms, there's actually another method of doing this where I call it the big picture method. Okay, instead of looking at how tension affects everything, tension's an internal force. It acts on both objects, but it's coming from a part of the system. Okay, and if we just strictly worry about forces coming from outside the system, okay, so anything coming from outside the system is what's going to cause things to happen. Well, there's one here.
Just gravity.
Just gravity, m2g. And there's technically two here, but they balance, right? You've got the normal force and gravity here, but they balance. So I don't have to worry about them. Which means if I use Newton's second law, net force equals mass times acceleration, my net force
is actually
m2g.
That weight, because that weight is going to make it accelerate.
Right? And my mass
is m1 plus m2.
The total mass, m1 plus m2. And my acceleration is just acceleration.
Oh, so we got the same equation.
Exact same equation.
Hey, I like that method a little bit better if we can just remember that the weight of m2 is what's making us accelerate.
There we go. Okay, so same equation, much faster. Okay, but you can go through and find tension as well. And sometimes the tension in the string actually is important. It's causing some other thing to move or whatever. And so once you have acceleration, then you can go back into either one of these, right? Then you can say, hey, the net force here is actually T, so Ft equals m1a. And since you have this acceleration, you can find tension.
Then we can do that, yeah.
So you can go both directions with it.